Non-homogeneous reconciliation. So what is a non-homogeneous case? Non-homogeneous means Fn in your general equation, that is C naught an plus C1 an minus 1 plus etc. Ck an minus k is equal to f of n. That f of n is not equal to 0. That is, it is a function in terms of x there. That it can be it can be any term, it can be a function in terms of n there, it can be a polynomial in terms of n, such that. So, the solution of the above equation, that is C naught an plus C1 an minus 1 plus etc. Ck an minus k is equal to f of n, where f of n is not equal to 0 and Ci's are the constants there. So, the solution of the above equation will be given by an is equal to anh, that is homogeneous case, plus anp, where anh is the solution of the associated linear homogeneous reconciliation and anp is the particular equation there. Now let's see, as seen before, for non-homogeneous case also we will have certain cases and we have the corresponding trial solution. B raised to n, that is, if b is not the root of the characteristic equation, b raised to n, if your f of n is equal to of the form b raised to n, where b is not the root of a characteristic equation, then your trial solution, that is a and p, is equal to capital A b raised to n then. Next, b raised to n. If b is a root, what happens if b is a root of multiplicity L there? Then a times n raised to L into b raised to n. L is the multiplicity there. How many times that root have been repeated there? Okay, next is a polynomial, that is p of n, a polynomial of degree n. So your trial solution will be a naught plus a1n plus etc. am n raised to m there. Now c raised to n times your polynomial, c, where c is a constant and c is not a root of your characteristic equation, then c raised to n into a naught plus a1n plus etc. plus am n raised to m then. Now if suppose c is a root, what happens? Of multiplicity L, c raised to n p of n, where c is a constant and c is the root of multiplicity L. Then what happens? So your trial solution will be of the form n raised to L, c raised to n into a naught plus a1n plus etc. am n raised to m then. Now let's see some problems. Okay, your first problem is solve the non-homogeneous reconciliation, that is yn plus 2 minus yn plus 1 minus 2 yn is equal to n square, that is your f of n is a polynomial there of degree 2 there. So your solution will be yn is equal to ynh plus ynp there. Okay, so the homogeneous, your general solution will be, you have to find yn, what is ynh and ynp there. So first we'll find what is ynh, that is homogeneous case. How will you do our homogeneous case? We'll equate that right hand side to 0 there. Okay, that is yn plus 2 minus yn plus 1 minus 2 yn is equal to 0. We'll find the characteristic equation, that is r square minus r plus 2 is equal to 0, and we'll find the corresponding characteristic root there. What is our characteristic root here? R is equal to minus 1 by minus 1, 2 there. They are distinct and real. So your ynh will be of the form c1 into minus 1 raised to n plus c2 into 2 raised to n. So this is your ynh. After finding ynp only, you will be able to find what is our constant c1 and c2. So to find a particular solution, fn is equal to n square. N square is a polynomial of degree 2. So we will consider the trial solution. We will have the trial solution as a naught plus a1n plus a2n square. Now we are going to substitute this in our equation. That is, what is our equation? Equation is, what is our equation? Yn plus 2 minus yn plus 1 minus 2 yn is equal to n square. So while substituting, first you have to substitute, that is, while substituting this trial solution in your equation, a naught plus a1 into n plus 2 plus a2 into n plus 2 whole square minus a naught plus a1 into n plus 1 plus a2 into n plus 1 the whole square minus 2 times a naught into a naught plus a1n plus a2 n square is equal to n square. Now you will compare the n square term, n term and the constant term, and you will be able to find what is your a naught, a1 and a2 there. Substitute that a naught, a1, a2 in your trial solution, that is ynp is got as minus 1 minus 1 by 2 raised to n minus 1 by 2 raised to n square. So you obtained what is your ynh and ynp. Now sum that and that is yn is equal to c1 into minus 1 raised to n plus c2 into 2 raised to n minus 1 by 2 n minus 1 by 2 n square. So you have to know what the trial solution is, substitute that trial solution to get your a0, a1, a2 in your equation and find what is a0, a1, a2 and substitute the values of a0, a1, a2 in your trial solution and get your y and p, and then you have to find that you will get the general solution as yn is equal to ynh plus ynp. Okay, now let's move to the next question. Another one type. Solve an plus 2 is an plus 2 minus 5 times an plus 1 plus 6 times an is equal to 5 raised to n. Okay, so what happens? First of all, this is a non-homogeneous equation. Your function, that is your right hand side f of n is equal to 5 raised to n there. So you know that the general solution will be anh plus anp. We will find what is anh first. So accordingly we will write the characteristic equation, that is r square minus 5r plus 6 is equal to 0. That implies r is equal to, the characteristic roots are r is equal to 2 and 3, they are distinct. So anh is equal to c1 2 raised to n plus c2 3 raised to n there. Now you can see that here the root is 2 and 3 there, right? Now in order to find our a and p, your root is not repeating, right? It is br raised to n, that is it, right? So a and p will be of the form, the trial solution will be of the form a and p is equal to 8 times 5 raised to n. Substituting this a and p in your equation, that is our main equation, we will get a 5 raised to n plus 2 minus 5 times a raised to 5 raised to n plus 1 plus 6a 5 raised to n is equal to 5 raised to n. We can see that 5 raised to n gets cancelled throughout. So what remains? 25a minus 25a plus 6a is equal to 1, and you are getting your a as 1 by 6 there. So a and p is equal to 1 by 6 into 5 raised to n. Why did we take this trial solution as a 5 raised to n? Because here r is equal, what happens, look, we have to check the table once again, that your roots are not repeating with your your function f of n, that is 2 3 is distinct from 2 3 is not equal to 5 there. Since that is the reason why we are taking a and p as a 5 raised to n there. So you get your general solution as c1 2 raised to n plus c2 3 raised to n plus 1 by 6 into 5 raised to n there. Now let us see the next question. That is, solve an plus 2 minus 4an plus 1 plus 4an is equal to 2 raised to n. Yes, that is again a non-homogeneous equation. So your general solution will be an is equal to anh plus anp. Your anh, in order to find anh, we have to take the equation, we have to equate it to 0. That is an plus 2 minus 4an plus 1 plus 4an is equal to 0. So the characteristic equation is r square minus 4r plus 4 is equal to 0. The characteristic roots are 2 and 2. That 2 and 2 is repeating with your function f of n there. So 2 is repeating 2 times there. So anh is equal to c1 plus c2n into 2 raised to n. Since 2 is repeating 2 is your root, as well as f of n is equal to 2 raised to n. So since 2 is repeating 2 times, the multiplicity L is equal to 2 there. So you have to take the trial solution as a and p is equal to 8 times n raised to L 2 raised to n. Your L is 2, so it becomes 8 times n square 2 raised to n. Now you have to substitute that in your main equation. That is your first equation. That is, then you will get 8 times n plus 2 the whole square into 2 raised to n plus 2 minus 4a n plus 1 the whole square into 2 raised to n plus 1 plus 4 times a n square 2 raised to n is equal to 2 raised to n. Put n is equal to 0 in your given the above equation. So you will get a as 1 by 8 there. So your a and p is equal to 1 by 8 into n square into 2 raised to n there. So the general solution is an is equal to, what is it, c1 plus c2n into 2 raised to n plus 1 by 8 into n square 2 raised to n there. So this is your fourth module. So we have discussed what the generating function is. We have seen the examples definition examples and the calculation techniques for the generating equations. Then we found what the exponential generating function is. We saw one problem there, and then we moved to the recurrence relation. In recurrence relation, there are first order recurrence relation and second order recurrence relation. We discussed both the homogeneous case as well as the non-homogeneous case. So that is our module number 4, and thank you. Thank you everyone.